All right, welcome back to part two of acid-base reactions and solubility. Last time we talked about buffers, and today what we're going to talk about is titrations. So those of you taking lab, it's really important that you listen carefully to this lecture. This will give you insight as to how to solve those titration problems and what data to collect when you're doing a titration, and give you some illustrations of what a titration curve looks like, and what we're looking for is that inflection point where we convert all of the acid that's in our sample to neutralize it, and then it becomes excess base in the Erlenmeyer flask. So really important lecture for those of you taking the lab and doing titrations. So we're going to focus on strong acid, strong base titrations. Those are the easiest. And then the weak acid, strong base, we're going to get into, once the acid's consumed, you have the conjugate base of the weak acid, which is going to react with water and form a basic solution. And then we have strong acid with a weak base, that's like the ammonium ion. And once the base reacts with the ammonium ion, then there's a weak conjugate, or fairly strong conjugate acid left over, and that will donate a proton to water and make an acidic solution. So that's what we're going to be looking at. So titration is really important. We use it a lot in chemistry. We want to find out the amount of unknown of something in our sample, and we're focused on acid base here, but there's plenty of different types of titrations. We're going to focus on acid base. So here we're trying to find out what was the acid concentration, the hydrogen ion concentration in an acid, or maybe the hydroxide ion concentration in the base. So a couple of things to point out. Just look at the equipment here, and I don't know if you're going to be using this equipment or not, but you will be using components of it. So one of the components you're going to be using is the burette, and hopefully you get a good burette. I know some people are taking the lab online, and I've seen the burette, and I'm not very crazy about it, but this is a burette, and then here's the stopcock, the valve that you use to control the solution that comes out the tip here. Here's your reaction vessel. And there's two ways to determine the extent of the reaction. One is what they have here is a pH meter. And so we'll be recording the change in pH as we add the titrant into the sample here. And so the other thing we can do, which is probably better for just one or two titrations, is to use a pH indicator. So the advantage of pH meter, if you're doing lots of titrations, once you calibrate the pH meter, then you can run through a lot of samples. But if you're only doing 1 to 3 samples, you're definitely more than likely, I don't know if you're going to spend the time to calibrate this pH meter. You're mostly going to use a pH indicator, and that will make it a little bit faster process. All right, the next thing is let's look at what a titration curve looks like. So you need to be able to read this plot. So here what we're doing is we are measuring the pH initially, and it's a pH of 1. So that tells us that we're dealing with an acidic solution. And so that means in our container here, we have an acidic solution. We're going to add the titrant into the acid. So we have an acid in here, and we're going to have a base in here. And the base is going to flow out into the acid, and then we'll stop once the pH indicator changes color, or we start seeing that the pH is not changing appreciably with the addition of the hydroxide ion. So what happens, as long as there's hydrogen ion present in the acid, it's going to react with the hydroxide ion of the base, and that's going to form water. So for a strong acid and a strong base, the equivalence point is going to be right there at pH 7, because at that point you've consumed all the hydrogen ion in the acid solution, and so what we have present, and all the base, we just add enough base to consume all the hydrogen ion. So all we have is water, and you know that the pH of water is 7. So that's called the equivalence points, when we've added enough of the titrant to consume all of the analyte. And so that's what this is called. That's another name for this, is the analyte, the substance you're interested in working with or finding out what the concentration is. Once we've used up all of the hydrogen ion, though, now the hydroxide ion, there's nothing for it to react with. And so that's why the pH changes drastically here. Like in one drop, it goes from here. I mean, look at the points. If I can erase those, that'll give you an idea how big the change is, how quick it is. And let me see if I can erase that. It's not going to let me do it. But there's a big jump there. And so then the more hydroxide we add, we don't really see much change in the pH. It does change a little bit because you're adding more hydroxide ion and you're increasing the volume of the solution, but that's about it. So this is what a titration curve looks like, where we start with the strong acid as our analyte in this container. We add hydroxide ion. At the equivalence point, we've added just enough hydroxide ion to consume all the hydrogen ion, and then the pH shoots up to above 7, a basic solution up here, because the active ion is the hydroxide ion. And you're going to be doing this in lab. The main thing is to make sure you get lots of data points. So if you're using a pH meter, which is what they're showing here, you would collect pHs after every so many milliliters of addition of sodium hydroxide. So they've got like what, 5, 10, 15, 20. Then they added more here because they knew it's about to change. So there's a lot more points in this region here. And then as it doesn't look like it's changing much, we can space out the additions of the hydroxide ion at the end. Make sure you do fill this out, though. I see some students, they want to stop right here after they see it doesn't change here to here that much. Go ahead and take you a couple more measurements out here just to make sure that's leveling out and nothing else is happening. So the type of reaction that we just looked at is a strong acid, strong base. And so in this case, we have sodium hydroxide, strong base, and then hydrochloric acid. That should be a lowercase L there, not a capital L. And again, what happens is, this is what I want you to remember about this. When you have a strong base reacting with a strong acid, you always, this is called a neutralization reaction. You get water, which is not an acid or a base, it's amphoteric, and you get a salt. And the salt, this is kind of what we alluded to in the last chapter. The metal ion comes from the base and the non-metal ion comes from the acid. It's important that when you look at this salt, you can tell me the acid and base that salt came from. It's not as big deal right here, but it will be as we get into the other variations of a weak acid with a strong base or a weak base with a strong acid. So again, if I'm doing a titration, I just draw a picture real quickly. Here's my burette, here's my stopcock, and then we usually use an Erlenmeyer flask. If you just want to use a beaker for your picture, my Erlenmeyer is not the greatest. That's what I would do. And it says consider the addition of 0.1 molar sodium hydroxide solution. So up here, the concentration is 0.100 molar sodium hydroxide. And down here we have 25 milliliters of 0.100 molar hydrochloric acid. All right, so we're going to see what happens when we start adding this sodium hydroxide in a measurable amount that we will measure off the burette and see what that looks like. Okay, so looking at this plot here, you can see that initially we have a 0.1 molar hydrochloric acid solution. Doesn't matter whether it's 5 milliliters, 10 milliliters, it's intensive, right? the concentration was 0.100 molar for hydrochloric acid. Hydrochloric acid is a strong acid, so that is the concentration of the hydronium ion. If we take the negative log of that, we learned that in the last chapter, we get the pH, and that's why the pH starts out at 1 right there. All right? That's before the addition of the base. All right, so we open up the stopcock and we add 10 milliliters of sodium hydroxide. All right, so we add 10 milliliters of 0.1 molar sodium hydroxide. So that's going to be this point here, right? 10 milliliters of sodium hydroxide added. Now they added one before that, but they're talking about this one. So they would like to know what happens here. And so what we're going to do here is we're going to multiply to make it easier for us. I think this is really important that you think about it this way. And some students will do this and some will not. But I tell you, it makes it much easier if you start working in millimoles here. Because all you have to do to get the number of millimoles of sodium hydroxide dispensed, you would say the concentration, 0.100, which is millimoles of sodium hydroxide per milliliter multiplied by 25.0 milliliters. So we know we set this up right. The milliliters cancel out. What we get for an answer here is millimoles, though. Okay? So 25 times 0.1 would be 2.5 millimoles of sodium hydroxide. Okay, and then let's see what the let's see here. All right, so that's what they're going to show here as well. All right, so let's see. So that's what it is at that point. If I divide the that's how much I dispensed. We know it doesn't consume all the hydrochloric acid because we started off with 25 milliliters of hydrochloric acid. So what you know at this point, let's just go and write this out too while we're at it. Let's go back. Let me go back to this slide here. So the amount of hydrochloric acid, which is kind of strange, but this is our first problem. You know how many millimoles of hydrochloric acid's in the flask because you can say 0.100 millimoles of hydrochloric acid per milliliter. And then you've got 25 milliliters. So you know that at 0.1 times 25 milliliters, you have, oops, we got 10 milliliters. Let's see. Did I do that wrong down here? I did this one wrong down here. So, yeah. This should be 10 milliliters here. All right. And that makes this 1.0 millimoles. But what you have in hydrochloric acid is 2.5 millimoles. So the 1 millimole of sodium hydroxide reacts with the 2.5 millimoles of hydrochloric acid. And so what you have left is you have 1.5 millimoles of hydrochloric acid. And then watch what happened to the total volume. You had 25 milliliters of hydrochloric acid. You added 10 milliliters, so that makes the total volume 35 milliliters. And then you could make that into a concentration, 1.5 divided by 35, and that would give you the molarity of the hydrochloric acid. And you could take the negative log of the hydrogen ion concentration, and that's how you would get that number there, the pH slightly larger than 1.0. So that's what you're going to be doing a lot in titrations is multiplying concentration times volumes and figuring out how much of the hydrogen ion or hydroxide ion is free in the solution. And then if you know what the hydrogen ion concentration is, you take the negative log of it and get the pH. Or if you know what the hydroxide ion concentration is, you can take the negative log of that and get the pOH. So that's what we're going to be doing in titrations. And what made me catch the mistake here was when you first add sodium hydroxide, you don't want to add so much sodium hydroxide it consumes every bit of the hydrochloric acid. You want some points out here where there's still hydrogen ion present. And then right here is where you've just consumed all of the hydrogen ion by the addition of the hydroxide ion. All right, so the next case after that is to look at, let's see, next slide. We're going to add more sodium hydroxide. So what they say here is right before the equivalence point. So here's what we have. We now have a total volume of 35 milliliters because we had 25 milliliters of hydrochloric acid. We just added 10. And the number of millimoles of millimoles of sodium hydroxide in 10 milliliters was 1 millimole. All right, so we've done that. And then the original amount of hydrochloric acid, we did that, is 2.50 millimoles. So what we have left, this is just showing what I've been talking about, that you have 1.50 millimoles of hydrochloric acid left. And if we got 1.5 millimoles of hydrochloric acid left, if we divide that by 35 milliliters, that will tell us the concentration of the hydrochloric acid. And since hydrochloric acid is a strong acid, then we can calculate the pH. And so, again, this is the concentration of the hydrochloric acid. Let's see if I can draw that. Yeah. This is the concentration of the hydrochloric acid, which is the same thing as is equivalent to the concentration of the hydronium ion or hydrogen ion. If I take the negative log of that, the pH is 1.37, and that's why you see this just a little bit higher than 1. Okay, so that's what we've just done. We've talked about what was added, calculated it out theoretically, then determined that the pH should be 1.37, and we made a plot there. Or a point. So the next thing we're going to do is what happens when we add just enough sodium hydroxide to completely consume all of the acid. So notice what we have here. We have 25 milliliters of 0.1 molar hydrochloric acid in the flask. We've added from the burette 25 milliliters of 0.1 molar sodium hydroxide. So at that point, the hydronium ion and hydroxide are equivalent. They're equal to each other. And we're exactly at, when those things are equivalent in water, we're exactly at a concentration of 1.00 times 10 to the negative 7th. And so the pH is 7. And there's the equivalence point right there. And that's, see, notice right here, this is 25 milliliters right there of sodium hydroxide added. And so the equivalence point occurs when we've just added enough hydroxide ion to consume all of the hydronium ion. So the next thing is that what happens when we add more sodium hydroxide? So here you can see when you take this times this, that's going to give you 3.5 millimoles of sodium hydroxide. And you only had 25 times 1, you only had 2.5 millimoles of hydrochloric acid. So now you have excess. So if you subtract that, you'd have 1 millimole of sodium of hydroxide ion or sodium hydroxide. And the total volume now is the 25 plus the 35. That's 60 milliliters. So if I take the 1 and divide it by the 60, that will give me the concentration of the hydroxide ion, since that's what's present in the greater amount. The hydrogen ion has been consumed. So let's look at that. So that's what we get. We get a, and this is where most students make a mistake. So I just want to point out something right here. So we just found out we had 1 millimole of excess sodium hydroxide divided by the total volume now of 60 milliliters, and we come up with this concentration. What is that the concentration of? Don't just write the concentration. Make sure you write it what it's of. And then that's going to be the same as the concentration is going to be 0.0167 molar, that's a word, 7 molar hydroxide ion. If you take the negative log of this, you're not calculating pH, you're calculating POH. So be careful. Once you've added an excess amount of the base into the acid, all the acid is gone. All the hydronium or hydrogen ion is gone. Now you have excessive amount of base. And when you take the negative log of that, that's no longer the pH, that's the POH. So that's the most common mistake if you're not following along what you're doing. All right, so notice they tell you you're determining POH, not pH. If you want to know what the pH is, you take 14 minus the POH, and that gives you the pH. So right here, you can follow this out at, we've added 35, we're right here, right? We've added 35 milliliters of sodium hydroxide, and right there's our point, right there, and they tell us that it's 12.22, so that point should be a little bit above. Oh no, yeah, it should be a little bit above that number right there. It doesn't quite look that way. It looks like the 40s more like it, but that's okay. All right, so the pH at this point is not 1.78. That's the POH. But generally we ask for the pH, and the pH is 12.22. So don't make that mistake. Notice the equivalence point is at 7 because we're titrating a strong acid with a strong base. So you're going to be collecting data like this in the lab if you're doing titrations. So you'll have initially, you will have, let me get this slide over here. You'll initially have 0 added of the titrant, the sodium hydroxide. We maxed out at 25 milliliters of sodium hydroxide added. Well, actually it continues on to 50 milliliters, right? So this is one column, that's the next column. All right. No, that's the total volume. So this is right. We just maxed out at, well, they go here. They go to 35. There we go. So what they're doing here is, this is the equivalent point right here. We've added just enough sodium hydroxide to consume all the acid. There's no acid left. And so that's why the pH is 7. Beyond this point, we have an excess of the hydroxide ion. And we're not measuring pH, we're measuring POH that we will convert to pH. So your data in the lab should look similar to this, where you're recording step by step how much sodium hydroxide you're adding. And then you're going to talk about the consumption of the, we initially have 2.5 millimoles of hydronium ion in the flask, and notice it goes to 0, and then beyond that point we're just dealing with hydroxide ion in solution. So look at the data here. This is what you should be doing in the lab as well. And one other thing, I guess, before we move on, just look how the pH changes. We are very acidic. We get to neutral, that's the equivalence point, and then beyond the equivalence point, we're definitely a basic solution because there's no hydrogen or hydronium ion to react with the hydroxide ion. All right, so our next scenario is what happens when I titrate a weak acid with a strong base. All right. So we're still in the flask. We have a weak acid, and you go, how do you know? Because the pH is acidic here. We're going to end up with a basic solution at a pH just above 12. And notice the equivalence point, though. This is the telltale sign you're not dealing with a strong acid with a strong base, because if it was a strong acid with a strong base, the equivalence point would be at 7, and this one's at about 8.5 here, 8.5. So that tells us that this is not a strong acid with a strong base. And in fact, it tells us this curve is a strong base with a weak acid. And what's going to happen is that the conjugate base of a weak acid will react with water and form the weak molecular acid and generate the hydroxide ion at the equivalence point. And so that's why the pH is a little bit higher than 7, because it's going to generate the hydroxide ion and make a basic solution. So we're going to see an example of this so you'll get the hang of it. So let's look at this. So we have acetic acid. You should know this formula for acetic acid. You might know it is also HC2H3O2, but you need to know acetic acid. And you need to know that's a weak acid. It's not one of the 7 strong acids you have to memorize. So we got a weak acid and a strong base. And what happens, as long as this base is present, this hydrogen ion is going to react with the hydroxide ion, and we're going to form water. And then the sodium ion is attracted to the acetate ion. Now, this stays dissolved in water. How do you know? Because it says aqueous here. And if you don't know the solubility rules in chapter 4 of this book, you may want to go back and brush up on the solubility rules. So any acetate compound or any compound that contains the sodium ion is water soluble. So as long as this acid is present and we add base, the hydroxide will react with this and form the salt and water. This is a salt. There's a metal ion, and then this is a nonmetal or polyatomic negative ion here made of nonmetals. But here's what happens. At the equivalence point, all of the hydroxide has consumed all the hydrogen ion. And so what you have left is, you could write this as sodium acetate if you wanted to, and you can turn it around if you want to. If you want to write it like this, you could do that as well. I don't know if I would do it that way, but that you could do that. And then this sodium acetate, it's water soluble, so it stays in the form of sodium ions and acetate ions. And then what happens is the acetate ion is the conjugate base of the weak acid, acetic acid. So when given the opportunity to react with water, it will form the molecular acid. So that hydrogen ion comes off of the water and goes here, plus the hydroxide ion. And if we're generating the hydroxide ion, it's going to be a pH greater than 7. So that's what's going on here, is that when you titrate a weak acid with a strong base, once all the base heats up the acid, then you have the conjugate base left over, in this case the acetate ion. And we know that the conjugate base of a weak acid is a fairly strong conjugate base. It will accept a hydrogen ion from the water, form the molecular acid, and generate the hydroxide ion, giving us a basic solution. All right, so here comes the ice table again. So you want to be able to do an ice table. And so our ice table looks like this. Initially, we have acetic acid. And initially, we have nothing else. And so the acetic acid, we're going to lose X amount of it. We're going to gain X amount of the hydronium ion, X amount of the acetate ion. And then here's our equilibrium values. Okay. So why are they showing this? Well, they want to show you the dynamics of just the weak. This is kind of a refresher from the last slide. The last chapter. So we know how to do an ice table for a weak acid. It looks like this, and we have our products over our reactants. and we have x squared over 0.10 minus x. That's our equilibrium value for the acetic acid. We're going to assume this x is negligible. Okay, so if we do that, and then 1.8 is the Ka, or the acid ionization constant for acetic acid, 25 degrees Celsius. So when we solve for this, we're going to get x equals 1.34 times 10 to the negative third molar. Okay. So you go, why did I do this? Because if I take the negative log of this number here, then that is the hydronium ion concentration. If I take the negative log of this, I get the initial value of 2.87. So that's where we are. Nothing but pure acetic acid with a concentration of 0.10 molar. If it's a strong acid, 0.10 molar would be a pH of 1. Because this is a weak acid, it doesn't completely ionize. Its initial pH is 2.87 because it stays in the molecular form. It stays in the form of CH3. Most of it stays in the form of CH3COOH. Doesn't generate. And that's what we saw in the ice table. All right, so what happens if we add some base to this acetic acid? Well, that's what this is showing. The base is going to react with the hydrogen ion and form water, and it's going to leave us the acetate ion. Now, before the equivalence point, there's always going to be acid that can be converted, and so that's why the pH slowly creeps up, but it's not drastically changing as long as we have some acetic acid present. All right, so this says the solution is a buffer, and we use the Henderson-Hasselbalch equation to calculate the pH. After the addition of 10 milliliters of base, the solution contains 1.5 millimoles of acetic acid and 1 millimole of acetate ion. Okay? So what they're saying here is that when we add the base, we lose some acetic acid, we generate some acetate ion, and so we can use the Henderson-Hasselbalch equation to determine what the pH is after the addition of 10 milliliters of base. So right here, the pH is 4.56. Okay? And we use the Henderson-Hasselbalch equation to do that because remember what the Henderson-Hasselbalch says. This is my conjugate base. This is my acid. And the volume is the same. Both of these amount of moles are in the same amount of solution. The total solution is 20 milliliters, I guess. And so 10 milliliters of that and 10 milliliters of the other. All right, so we'd have, and so we can calculate the pH at this point using the Henderson-Hasselbalch equation. That is the quickest way to determine that pH. And where you get the 4.74, that's that negative log of 1.8 times 10 to the negative fifth. All right, at the equivalence point, that means we've added just enough base to consume all of the acetic acid. So that's at 25 milliliters here. So what's happened here is you've got the acetic acid, you've added enough hydroxide ion to consume all of the acetic acid. So what you have at this point is H2O plus the conjugate base acetate ion. The acetate ion, which is a conjugate base. All right, so it says all the acetic acid's been consumed or neutralized, and we are left with just the acetate ion, and the pH is determined by the concentration and the Kb of the acetate ion. So we've seen this, but let's reiterate it. So you're going to take the acetate on and you're going to react that with water. Okay. So let's see what they did here. So the amount of acetate on you have formed is 2.5 millimoles, and the total volume now is 50 milliliters. Because you've added, the equivalence point occurs at 25 milliliters. Yeah, and I guess you had 25 milliliters of acetic acid solution, not 10, like I said the other. So total volume is 50 milliliters. So if I take the moles of acetate on at the equivalence point, divide it by the total volume, I get the concentration of the acetate on. Not worried about the sodium ion, doesn't interact with water, but we know that this acetate on is the conjugate base of a weak acid, which is acetic acid. And we know that if I put that conjugate base in water, which it is going to react with react with water. And so that's what this next ice table is. So notice we changed the equation. No longer acetic acid reacting with the base. It's the acetate ion forms water, reacts with water to form hydroxide ion and the molecular acid. And initially, that's what the concentration is at the equivalence point. That's the concentration of the acetate ion, and the hydroxide's been consumed, so it's 0, and the acetic acid, which was originally present in the flask, is 0. And then we know the reaction has to go this way because Q is less than K, and so we're still using reaction quotient even today. And we know that this is the expression that we're going to write. It's products over reactants, and because the hydroxide ion concentration is in this expression, we know that we need the Kb, not the Ka. So to find the Kb, we learned that Kb equals 1 times 10 to the negative 14th divided by the Ka. That's how we get this number here. We plug in these X values here, and the acetate ion at equilibrium there, 0.050 minus X. We're going to assume that X is negligible because this K is so small, right? This basicity constant is so small. We know it's not going to go much to the right. All right, so when we solve for X, we get 2.8 times 10 to the negative 11th. This is where most students make a mistake right here. What is this? What is that value? What does X represent? Well, you have to go back. You have to go back and look at the ice table to see what X represents. And so when we go back, we see that X doesn't represent the hydronium ion. It represents the hydroxide ion. And it represents the molecular acid. So when I get to this point, I know that this is equal to the concentration of the hydroxide ion, and therefore, well, that's this. Yeah, I got to take the square root of that. So we go down here. That when I take square root of that number, I get the concentration of the hydroxide ion, and then I take the negative log of that. I get a POH, not a pH, a POH of 5.28. I subtract that from 14.00 and I get a pH of 8.72. So that's how we get that number right there, 8.72. The sodium hydroxide has consumed all of the weak acid. What we have left is the conjugate base. We set up an ice table with the conjugate base reacting with water, which it does because the weaker the acid, the stronger the conjugate base. That's why we do this table up here. And then we do an ice table like we learned in chapter 15. We solve for X. Luckily, this X is negligible. Why is it negligible? Look how small that K is. Look how small that base constant is. It's so small we know this reaction's not going in the forward direction very much at all. All right, there's my expression. I plug in the values. I solve for it. And again, most common mistake is this. People don't go back to the ice table and make sure what that refers to. It's not the hydronium concentration. It's the hydroxide. You have to take the negative log of that to get this, subtract that from 14 to get this. If you do that, you'll be fine. All right, after the equivalence point, so we know the pH is going to be up. It's going to be above 7. It's going to be an acidic solution. And it says because all the acetic acid's been consumed, there's nothing for the hydroxide ion to react with. And so the pH level's off at 12 or 13. Again, there's no conversion of hydroxide. So again, we've seen this before. It looks exactly like what we saw on the other one. The only difference is here we start with 0 additions of the hydroxide ion from the sodium hydroxide. And initially we have 2.5 millimoles of the weak acid. When we add 25 milliliters of this 0.1 molar, that's our equivalence point. That's where we've consumed all of the acid. Beyond 25, which is what these two are showing, there's nothing to react with the hydroxide ion. So that's why the pH changes drastic, or POH or pH, either way you want to think of it, changes drastically here, because now we have free hydroxide ion and we don't have any acetic acid to neutralize it. So that's why you see this big jump here between 25 and 30. We see that the POH goes from, well, they don't even show the POH. They show the pH goes from 8.72 to 11.96. And then we add 5 more milliliters of sodium hydroxide. There's nothing there for it to react with, so that increases the hydroxide ion concentration dramatically. And we divide that by the total volume of the solution. We get this for the hydroxide ion concentration. We take the negative log of it, and we find out the pH is 12.22, which is higher than this one. And it should be, because we have more hydroxide ion present in solution. The main thing I want you to get out of this is I want you to be able to do a titration plot. But just remember, if it's a strong base with a weak acid, the equivalence point is going to be above 7. You can actually figure it out, but it is going to be above 7. And if it's not, you've made a mistake, because if it's a strong base with a weak acid, then you know the conjugate base of the weak acid will react with water and form the weak acid, and I should use double arrows here, and the hydroxide ion. And that's why this pH is a little bit greater than 7. It's 8.72. All right, so here's a problem for you to try. So I would just stop the video. I'd try to work this out, see what you can do, and see if you get the right answer here. All right, let's go through this one, and then we'll quit after this. Oops. So it says calculate the pH of 50 milliliters of 0.120 molar acetic acid by 0.240 molar sodium hydroxide after the addition of 10, 25, and 35 milliliters of base. So what I would do, just to kind of center me here, I'd draw a picture. Here's my burette. You don't have to draw an Erlenmeyer flask. You can draw a beaker if you want to. Inside this beaker, you know there's 50 milliliters of 0.12 molar acetic acid. So it's 0.12 molar times 50 milliliters. And that's going to tell me how many millimoles of acetic acid is in my container initially. And I know initially the volume's 50 milliliters, so if I take the, I can solve this for like an ice table and figure out what the concentration of the hydronium ion is and calculate what the pH is. So the question is, what is the, once we add the 0.240 molar sodium hydroxide, which is a strong base, in these increments, how does it affect the pH? So draw a picture. I think it's worth a lot to do that to see what's going on. So here's what's going on. Let's write the equation. It's the acetic acid in the container reacting with the hydroxide ion of the strong base. Notice the sodium is a spectator ion is taken out. That forms water and the conjugate base of the weak acid, which is the acetate ion. So you've set up an ice table. What they have is the millimoles of all the substances. So they're saying that it was 0.120 millimoles and you had 50 milliliters, so that means you had 6 millimoles of acetic acid. You know how many millimoles of hydroxide you added? And so and then we assume, let's see, we assume initially 0 of that. This thing's kind of offset. Remember, this doesn't even play in it. It's constant. Yeah, that's kind of deceptive there. All right, so after this has been consumed, you have 3.6 left of this. You have all of that being consumed, and you should have 2.4 millimoles of this over here. I don't know if there's a typo there or something. This doesn't matter. We're not worried about the water, and so at 0, I don't know why they had that. I thought it was for the water, or well, I knew it was for the acetate up here, but I don't know what they're doing there. A little bit of a typo, maybe. All right, so here's the fast way to solve it. What you do is you take the amount of conjugate base left over. Oh, that's what this is. So that's how much conjugate base left over. Divide it by the acid, and then the pKa of acetic acid is 1.8 times 10 to the negative fifth. And so if we put that in equation form, it looks like that. Okay. So pKa plus the log of 2.4 millimoles over 3.6. And you say, aren't these supposed to be concentrations? We get away with this here because the total volume is the same for both of these. They divide out, so that's why they're not writing them there. The pKa of 1.8 times 10 to the negative fifth is this number. The log of all of this is this number. And so we subtract that from 4.74, and the pH has gone from 4.74 to 4.56. Okay. After the addition of 25 milliliters, the next thing you do is you know how much you've added. You know what the volume is. The concentration is 0.240. So 25 times 0.240 gives us 6 millimoles. And so the volume is 6 millimoles divided by the concentration. We've added 25 milliliters. That's the way you check. So it says after the addition of 25 milliliters of base, the titration is at its equivalence point. Calculate the pH using the Kb. So at the equivalence point, what we have is we have the acetate ion reacting with water to form the acetic acid, but it's in its molecular form, plus the generation of the hydroxide ion. So this solution is going to be basic, and that's why they tell you you need the Kb of the acetate ion to solve this problem. All right, so here's what our ice table looks like. So notice the equation is not acetic acid anymore. It's the acetate in water, forms the hydroxide ion, forms the acetic acid. This is what the concentration is. Take the 6 millimoles of acetate ion, divide by our total volume now of 75 milliliters. That's the concentration of the acetate ion. Because these are 0 initially, we know that Q is less than K, and we know this reaction is going to go in the forward direction. So we know it's minus X amount of this, plus X amount of that, plus X amount of that. And this is my equilibrium values. So I'm going to take that, and I'm going to plug it into my expression. And the expression is Kb equals the acetic acid times the hydroxide ion concentration over the acetate ion, just like we saw in the equation. We assume this is x is negligible, and we solve for x, and we get 6.7 times 10 to the negative 6, which is the hydroxide ion concentration. So if I take that hydroxide ion concentration, plug it into the negative log, that gives me the POH, and then subtract that from 14, I get the pH of the solution. All right. So the key here is once you've consumed all the acid, then what happens is the acetate reacts with water and forms acetic acid and the hydroxide ion. So that's what happens when you have a strong base with a weak acid. And it's going to cause the equivalence point to be above 7. It's going to be a basic equivalence point. All right, so at 35 milliliters of base, we've consumed every bit of the acetic acid, because we've added 8.4 millimoles of hydroxide ion. 8.4 millimoles of sodium hydroxide, which is equivalent to 8.4 millimoles of hydroxide ion. So 8.4 minus the 6 millimoles of acetic acid that we started with says that we have 2.4 millimoles of excess hydroxide ion that is not reacted. If we divide that by the total volume of the solution, that will give us the molarity of the hydroxide ion. So let's do that. All right, so 2.4 divided by our new total of 885 milliliters, 85.0 milliliters. And so we get a hydroxide ion concentration of 0.0280. Take the negative log of that, and that gives me the POH. Subtract that from 14 gives me the pH, and there's my answer. So just make sure you do these steps here, because I see students work through this and they solve for x and they get x correct, but then you got to plug it in the ice table to see what it represents. In this case, it represents the hydroxide ion concentration. So I take the negative log of that, that's POH, but I want the pH, so 14 minus the POH gives me the pH. So that's what we're doing there. All right, so this is a strong acid with a weak base, and I'm going to stop here. I'm going to break this down. We've already gone 53 minutes. It was pretty intense. There's a lot of steps in these calculations, so we'll stop here, and I'll pick up from here on our next video. Thanks.